Hello React Native developers, I hope you are well. William here, recording from beautiful Zurich, Switzerland. I have something so special to show you this morning. And well, let's just have a look. 6 years ago, we were running the Can It Be Done in React Native YouTube series, where we were puzzling our way towards A-grade user experiences using the little to no graphic primitives we had. Come to think of it, the show was running under a simple premise. The bigger the obstacle, the bigger the fun. But eventually, we need to go from playing with the obstacle to overcome it completely. And with Christian Folk, we brought Skia to React Native. You have used it to build award-winning user experiences, and we are building it to follow the symmetry with the web, which led us to WebGPU, allowing us to compose nicely 3D scenes and 2D scenes together. And that was phase one of the project, to bring web graphic primitives to React Native. Once we had Skia in native, we realized that what we had was much better than web graphic primitives. On the web, web graphic APIs are completely siloed with one another. SVG, shaders, Canva 2D. This is when we started to work with React Native Skia Web, allowing us to have a unified API between all these important graphic primitives, allowing us to build, for instance, incredible graphic motions using Remotion. And that was phase two of the project, to bring native Skia API back to the web. So we went from the web to native to bring these nice graphic APIs, and then from native back to the web to use the nice Skia API. So what are we going to do now? Go back from to... All the work we've been doing so far was done under one assumption. One maybe fatal assumption. We assumed that web graphic APIs, as siloed as they might be, represent a full set of 2D primitives. But do they really? Let's have a look. On the web, you can set a stroke and a fill color, and that's pretty much it. The stroke width is a fixed scalar value. It's not really possible to have the stroke width be variable based on geometry information, like in this example where the stroke width is based on the tangent of the path. And the access of geometric information you have is very crude. For instance, you can shade the path using a linear or radial gradient, and that's pretty much it. You cannot have a gradient follow the arc length of the path nor its distance. And it gets worse, that geometric information, as crude as it might be, at some point in the pipeline gets completely lost. In SVG, image filters are arguably the most powerful feature, and they rely 100% on raster information, which is somewhat ironic because SVG stands for Scalable Vector Graphics. This is an example of a user interface heavily relying on a large amount of raster blurs. That interface can get very slow very quickly. And on the right side is the same user interface where the soft shadows are computed purely based on vector information. No rasterization step, just a single render pass running at full frame rate. And of course, using vector-based blur, you can build advanced effects which are simply not possible using raster blurs. One last example, if you'll indulge me, physics-based renderings. To build a PBR in SVG, you need to provide height information in the form of a bitmap. And that's really ironic because all you really need is plain, rich geometric information, nothing else. The idea that we will go through a rasterization step here feels very awkward. Finally, to build a custom effect, you need to use shaders. And shaders require you to use a specialized GPU language, which would be okay, but the mindset is completely different. In TypeScript, you issue drawing commands, and we take care of showing you the right colors at the right pixels. In a shader language, everything is flipped on its head. You get an XY coordinate, and you have to walk back the path to the color you want to achieve. So maybe here there is a gap that could be solved. And that's a taste of the problem space we are looking at. Crude geometric information, effects which are purely based on raster information rather than vector information, and custom effects which live on a completely different universe. So here's what we're going to do. This morning, I would like to introduce a new grade of 2D primitives for native and web. Thanks to WebGPU, these primitives are going to integrate at zero cost with existing libraries such as Skia and Free.js. This will kickstart phase 3 of our quest towards delightful user experiences, and this is how it looks like.
Is that the new? Is that the new you? Coming in hot, look what we got. Are you ready? Set, go.
So, a new grade of 2D primitives, Project Redraw. Let me set the scene. Currently, we have 2D primitives, which are extremely easy to use, but somewhat limited. And then you have GPU programming, which is incredibly powerful, but extremely hard to use. Our goal is to provide an easy-to-use API a la Canva 2D, but offering incredibly advanced 2D primitives. Now, when fiddling with new 2D primitives, you have to start at the beginning with Hello World. And for me, Hello World was a PostScript tiger. Each curve you see is rendered completely in real time on every animation frame. Some of you have seen this example countless times, but now there is a twist. You can now apply all sorts of geometric-based effects to the tiger. These effects are based on the rich geometric information of the Bézier paths. Ah là là, les courbes de Bézier. They are in fact the heart of the matter when talking about 2D primitives. And there are two kinds of Bézier curves, open paths and closed paths. Let's start with open paths. I have my SVG path here, and I can set a stroke width. So far, so good. But now, check this out. Instead of passing a scalar value for the stroke width, I can now pass a function. That TypeScript function will run directly on GPU using typeGPU. That function can describe any arbitrary curve that will describe the stroke width of the path. As input parameters, we get rich geometric information that will allow us to build incredible effects. Here, for instance, we set a wavy pattern to the path based on the arc length of the path. Part of the rich geometric information we provide, there is also the tangent of the path which we can use. Here we set the stroke width based on the tangent of the path. Pretty cool, no? Finally, we can bind animation values to these functions that run on GPU. Here we have a progress value that we can synchronize to create an organic stylus effect. Now let's add some colors. In regular 2D world, you can set a unique color or a crude gradient to the path. But again, here, instead of a single color value, we can use a callback function, which will be compiled and run on GPU. I can, for instance, set the color based on the arc length of the path, giving me this beautiful gradient along path. Look at these beautiful self-intersections. If we were to draw the path using a distance field, this is what we would get. But we add the rich geometric information to the drawing, namely here, the path arc length that allows us to automatically deal with self-intersections. Another information available is the distance to the path stroke. Here, for instance, we can add a nice center line to the path. Finally, we can also use the tangent of the path to offset the white center line, giving a cheap physical rendering effect. Again, we can bind any animation values to these callbacks. We can use the progress value to shift the color gradient and fade the centered white line. Isn't that renderful? Now, these paths, they have one more trick up their sleeve. I mentioned that we nicely deal with self-intersections. They actually support opacity and can be blended with one another. This is particularly handy for physics-based renderings, such as this one. When Apple released Liquid Glass, all programming communities had fun replicating the effect. And that effect is based on rich geometric information. The way everyone worked around the problem, including us, was to use simple shapes. But of course, now that redraw provides us with rich geometric information on any paths, you can use any SVG path you would like to apply the glass material to it. And of course, you can build any physical-based rendering effects on these paths and even non-physically based renderings. These are the Bézier paths we know and loved, but infused with that rich geometric information. In 3D software, you have arbitrarily complex rendering capabilities, but your input primitive is really hard to harness. In regular 2D software, you have wonderful path primitives, but the rendering capabilities are extremely limited. And I just love the idea that we can now bring rendering based on rich geometric information to Bézier paths, which are such an ubiquitous primitive. So far, I've only showed you open paths. Let's have a look at closed paths. I can draw a path here, and I can have a nice PBR on it. I can do also something a little bit softer as well. Now, here's the kicker. I can blur the shape, but this is not a blur, it's a vector feather. There are no rasterization steps here. Let's use that blurred shape into this beautiful animation. Now, an animation, even as simple as this one, can easily drop frames on low-end devices. But of course, here, because we don't use any raster blurs, everything is very fast. Now, you can use vector feathering to build beautiful, soft, shadowy user interfaces. Again, an interface such as this one can quickly get slower on low-end devices, but not with redraw because there are no restoration steps involved. But I think that there is something much deeper going on here. Let me show you. Raster effects are slow and handcrafted. You need to build all the details manually. Now, some commercial products have long understood this problem and support vector feathering part of their offering. And they want you to rebuild the whole physical world yourself. I've watched many tutorials where you see industry experts painstakingly rebuilding the whole physical world themselves, one shadow at a time on every single shape. I do not believe that this sets a realistic expectation for developers and designers. What I believe is that instead, people are going to build simple and flat user interfaces, such as this one, and turn a knob to set the temperature on how realistic they want the rendering to be. Many people are going to learn to tasteful soft shadow rendering, and some might even build non-physical based renderings. Vector feathering is an incredibly powerful feature, but also because we keep that rich geometric information available, you can use it to build advanced physical and non-physical based renderings. We all have special relationships with raster effect. Now, what we did here is to ask the question, can we build similar effects using vector information instead of raster information? And we found some of the answers to be deeply meaningful. I'd like to show you a few examples. The first thing is that, of course, the feather is variable. The same way we can set a curve for a stroke width or a color, you can set a curve for a feather value. There are different kinds of feather effect. For instance, here we use a glow effect, or you can use an inner feather. This enables a new use case for real-time user interfaces, analytical motion blur. So here I can move my sticker around. I can give it a nice motion blur effect. I am exaggerating here for demo purposes, and of course, on top of the motion blur, you can add chromatic aberration. Here I am using vector feathering to build a backdrop filter. In regular 2D world, these are built by creating a new surface for each layer and doing raster effects plus composition. But in these examples, everything is computed in a single pass. This means that you can stack as many backdrop filters as you would like, and it won't affect performance. Now, to be able to show you all these demos, a couple of things needed to happen. The stars needed to be aligned, so to speak. And the first alignment is, of course, WebGPU. And for two reasons. First, WebGPU provides us with a unified runtime across libraries, so I can focus on building my own delightful primitives. I don't need to rebuild the whole world. These primitives are going to integrate at zero cost with existing libraries such as Skia or WebGPU. For instance, here we have a beautiful text layout rendered in Skia, which includes the native font rendering. And I can render a redraw path and nicely mask between the two. Isn't that cool? These are zero-cost integrations. The second reason WebGPU is so important here are compute shaders. WebGPU has two pipelines, a graphical pipeline and a general-purpose compute pipeline. And here, all the demos you've seen are used using compute shaders. This is not a new idea, of course, but I thought this was really fun and almost cheeky to think about what would happen if we build graphics using the non-graphical pipeline. And I found some of the answers to be extremely compelling. Now, a second alignment here is that at the heart of redraw is this ability to pass functions as parameters that will be compiled and executed on the GPU using typeGPU. And to tell you more about it, Ivo Plaza and Konrad Reshko from Software Mentioned.
Hello, future redraw developers. I'm Ivo.
And I'm Konrad.
And we're part of the typeGPU team here at Software Mentioned.
JavaScript callbacks are highly underappreciated. Higher order functions sit at the heart of every giant in the JS ecosystem. React, Vite, Express. The ability to hook into a library's lifecycle and run your own code is foundational to frameworks as we know them today. There is practically no escaping callbacks if JavaScript is involved. They are everywhere. Everywhere, that is, except the GPU.
Not having any callback support in shading languages greatly reduces the ability to build useful libraries in the graphics space. If you want to build a complex shader, you either have to build it from the ground up yourself, or copy an existing shader and change the parts that you care about. If instead a complex shader allowed you to hook into parts of its execution and deferred to you for the parts that you cared about, you would be able to focus on solving your specific problem and let it handle the rest in an efficient way.
So what if you combine geometry-aware shaders and callbacks? You get redraw. When you pass your shapes to redraw, it's able to draw them and apply complex filters and effects. By embracing typeGPU shader functions, redraw is able to defer to the user each time a shape's material is being determined, and call your callback for each pixel on the image. Thanks to the useGPU directive, your callback gets compiled into equivalent Wigzil code and is injected alongside the framework code, the same as if the framework author wrote and called those functions themselves. This gives you the flexibility of higher order functions without the performance penalty.
Let's go over a few shader features that typeGPU enables. Say you have a JavaScript function that accepts a number t and uses it to blend between the provided range of colors. We can visualize the output of the function on a single axis. You can see the colors are spaced apart evenly, and t determines which color to pick. If we land between the provided values, we blend the two neighboring colors depending on how far along t is between them. We first remap t from the range O1 to O colors.length. As you can see, the whole part represents the index of the color on the left of t, whereas the fractional part tells us how far along we are between the two neighboring colors. We use this information to retrieve the relevant color stops and blend between them with the standard mix function. If we instead wrote this function using Wigzil, we would have to concretize the length of the array the function expects as input, as well as each place the length is used in the function body. typeGPU allows you to write functions that are generic on the types of arguments, and it generates the adequate Wigzil functions for you, based on their usage.
To work around this without typeGPU, you could write a function that returns Wigzil, injecting constants where it needs to. But now you have a whole set of new problems to worry about. Each time you want to call a new version of this function, you have to remember to add it to the definition list. And each time you stop using a specific version, it sticks around in the shader code until you become aware that it's not being used anymore. And one of the number of colors you want to mix is determined at runtime, based on controls you give to the user. You now have to make sure that you are not duplicating the definition of interpolate colors free when the user happens to pass in free colors, which would cause a shader compilation error. So hopefully now you can see how typeGPU and TypeScript shaders in particular are able to help you with managing complexity in your app.
But there is one advantage that shader languages like Wigzil have over TypeScript: the ability to use regular operators with vectors and matrices. But since we're already transforming your code at build time, we provide an optional drop-in replacement for the TypeScript language server called Solver. Everything still works the same, but now you can add and multiply and do whatever you want with vectors and matrices inside shader functions. As you can see, the code becomes much more readable and manageable.
Shared helpers that don't depend on GPU resources can be unit tested with no additional work required. This gives you the confidence that pieces of your code work correctly and you don't need to test your whole program at once. You can also individually compile specific functions to inspect what shader code gets generated. But sometimes you might want to inspect how the values behave on the GPU. For that, we support the JS developer favorite console log. It's not often that you see a Unicode string used in shader code. Another place you might see this happening when you look at redraw's documentation is the color function, which can accept a color hex code or a CSS color name. Both of these features are possible thanks to a new typeGPU feature we're very excited about: comp time expressions. This essentially means that you can mark code that's supposed to run during the shader generation process before it even reaches the GPU. If you're interested, you can read more about this in our documentation at typegpu.com.
And with typeGPU, you aren't limited to just a single callback. You can split your shader up into multiple functions or even multiple NPM modules. As we build out new tech demos, we collect functions that we think might be useful for others and package them up as new libraries. Let's name a few that you can play with today. typeGPU noise gives you pseudo-random number generation, similar to math.random, and procedural patterns like Perlin noise, which allow you to express organic-looking patterns in your shaders. typeGPU SDF gives you access to distance functions for lots of shapes, commonly used in rendering crisp UI or geometry that is hard to represent with polygons. And there's many more, with lots coming in the future. And while redraw is built from the ground up to work with typeGPU, you can also use typeGPU shaders with other libraries like Free.js or Pixie.js. Check out our integration guides on typegpu.com.
We are really happy to be a part of this new project. A tool that feels as familiar as React Native Skia, but opens up new possibilities in terms of effects and composability.
TypeGPU out. Back to you, William.
Thank you, Conrad and Ivo. This looks really cool. I really love that this is a bundling dependency. There are no heavy runtime dependency needed here, no heavy runtime compilation step. And of course, when writing shaders, operator overloading is very important. And there's something funny happening here. When I got started with Can It Be Done in React Native, a huge part of the series was reanimated. And Software Mention came up with a way to execute and compile JavaScript code on any arbitrary threads, which was a huge part of the series. So it was only a matter of fate that when starting to fiddle with GPU primitives, Software Mansion came up with a way to compile and execute JavaScript code to the GPU. With Skia and Reanimated is an optional dependency, but of course everyone is using it. And I think the same is going to happen here. typeGPU is an optional dependency to redraw, and operator overloading is as well optional, but I think that everyone is going to use it. And that's what I wanted to show you this morning, a new grade of 2D primitives, Project Redraw. Variable strokes, color along the path, variable blurs, physically based renderings as well as non-physically based rendering. The sky is the limit. And yet we keep the API as simple as the Canva 2D or Skia API. A key innovation for us to provide you with such a simple API is of course typeGPU that allows us to compile and execute JavaScript code on the GPU. And of course WebGPU with compute shaders and providing us a unified runtime across libraries such as Skia and Three.js. Now, as you can imagine, to develop an intuition such as this one, we needed a lot of time and space, and this wouldn't have been possible without your support. So this morning, we would like to make Project Redraw available as a technical preview to all startreactnative.dev subscribers. If you were a past subscriber, contact me and I will give you access to the project. Let me issue a heartfelt thank you to the community. These initiatives couldn't be built without your support. Now, when opening up a new area of work such as this one, I have so much more to tell you about it. And so I will, and I hope you can join me at App.js Conf on May 28th and 29th in Krakow or live on YouTube, where I will deliver an update on React Native WebGPU and React Native Skia, as well as key insight about the Redraw project. So yeah, I am looking forward to talk to you soon, and until next time, happy hacking.